We're ready. Good morning, everyone. I'm very happy to see you all here in place and welcome everyone in the network. My name is Michał Karpowicz. I'm Director for Research at NASK. Welcome to NASK seminar. I'm very happy that we are meeting today. We have a special guest, Keaton Ham from University of Texas, Arlington. I'm very, very excited to have Keaton here in Warsaw. Let me introduce Keaton with a few words and memories and a few words about his work. So as you well know, artificial intelligence is about processing huge amounts of data and extracting knowledge from the data. And mathematics is what makes it all work, and in particular, numerical linear algebra. And that's precisely the domain in which Keaton makes wonderful contributions. And in each domain, as you know, there are legends and icons and great names. And I will share a story that relates one of these great names with Keaton, and that's how I got to know about Keaton's work. As one of these names is Gilbert Strank from MIT mathematics department. A few years ago, Professor Strank wrote an email to me in which he wrote that I must read a brilliant paper that is very, very relevant. So when you get a mail of this kind, you immediately read the paper. And the paper was titled Perspectives on the CUR Decomposition. And it was written by Keaton. And immediately I understood why I got the email and why the paper is important. It's first of all, it's wonderfully written, and it made a huge impact on my personal scientific work and career, because it turned my attention to one of the most, I think, important algorithms in data science and numerical linear algebra that emerged recently. That's the CUR decomposition. That's one of this beautiful solution that lets you not only solve problems, but also understand the problems. Keaton will tell us more about it, but the paper shows how extracting knowledge from data and can be done. What is the role of this beautiful decomposition in all that, and what is the relation between matrix decomposition, optimization problems, and understanding of data. So it immediately, the paper written by Keaton immediately became one of my favorites, and it also started my own work in the domain. And then a few years later, Professor Strank wrote to me again an email in which he wrote, there's a brilliant paper that you must read. And that was a paper written by Keaton again, and it was about generalized pseudoskeletons, a paper in which Keaton generalizes the original ideas and concepts introduced in Perspectives on CUR. So this time I could not resist, and I contacted Keaton, introduced myself, and we had a great talk about mathematics, and we got to know each other a bit more, and then we connected in the internet, and that's how I made Keaton come to Warsaw. Keaton, thank you very much for accepting my invitation. Keaton actually is visiting us with his wife, Amy. And if you look at this wonderful paper on perspectives on CUR decomposition, you will see diagrams and graphics, and that was, I believe, made by Amy. So wonderful, wonderful work. Keaton, I'm very happy to have you here. The floor is yours. Welcome to Warsaw.
Okay. Well, thank you, Michał, for that extremely generous introduction. It's great to be here. Thank you all for attending. So I am going to talk about CUR decompositions and this general idea of getting more out of subsampling your data. Now, my title has matrices and tensors in it. For time reasons, I decided I'm going to focus primarily on matrix factorizations and techniques, but I will tell you that most of these ideas extend in a fairly natural way to tensor decompositions. So if you have questions about that, feel free to ask me at the end. So this is joint work.
Yep.
Maybe do we have another clicker?
I can also play the role.
Well, yeah, that would be, just make sure you're clicked onto the window.
Huh?
Here. Okay, yeah.
Yeah.
So this is joint work with a variety of collaborators. So people from all over. I'll list their names here, and then I have to thank our sponsors, the National Science Foundation and Army Research Office. So here's the premise where I'm starting from. In many applications, whatever your data looks like, and I will use that term very broadly, it could be a signal on a network, it could be images, it could be natural language processing data, whatever you like. I'll use that term fairly broadly. It's often true that if I have a data matrix, it is approximately low rank, so it can be written as sort of a sum of a small number of very nice rank 1 matrices plus some noise, and this noise may or may not have some structure that I understand. Later on I'll talk about sparse noise, or it could be Gaussian noise or things that I can model. Okay? And the sort of paradigm that I like to understand these problems under is, or like the way I like to solve these problems or approach these problems is that if I have a very massive data matrices and tensors, I'm going to use some nice facts from linear algebra about these so-called CUR decompositions to try to design algorithms that allow me to do whatever processing task I would like by only viewing a small subset of the matrix or tensor. Okay, so here I'm going to take a few columns and a few rows from my matrix, or maybe some tubes or slice fibers from my tensor, and that's all that I want to look at, and that's what I want to use to do my task. Okay, so that's the overall theme of this. So what is a CUR decomposition in general? I'll give you a couple of different perspectives on this. The first one, and this theorem, it's hard to trace exactly where it may have first been written. You can find traces of it in Penrose's work, even back in the 50s. And it's the following. So suppose I have this matrix here, and I extract some columns from it. For the moment, never mind how I do this, but I can tell you how later. And then I call that column submatrix C, so that's this red one here. And then I extract some rows from it, and I call that row submatrix R, so that's this one here. And then wherever they overlap, right, so I have red mixed with blue, so I get these purple entries here. So this matrix we call U. And the theorem says that if the rank of this small matrix U is the same as the rank of my full matrix that I've called L here, then L is the product of the columns and rows on the outside, and this U pseudo-inverse is what mixes them together. So this is the Moore-Penrose pseudo-inverse of U. Okay. As Michal mentioned, it is more general. You can get away with any sort of generalized inverse you want here, but for us, that's not so important. So for some general flavor of this area and what we're trying to do here, again, often we want to use these submatrices to reconstruct maybe a full data matrix or approximate a full data matrix. So one instance where this is common in machine learning is you have a large kernel matrix that you want to compute, but you cannot spend the resources to compute the full kernel matrix. So you instead compute only a few columns, and then you do this CUR decomposition to approximate the full kernel matrix. So for instance, some of my other work is in optimal transport-based manifold learning, and we want to compute an n by n matrix of Wasserstein distances, which is a distance between probability measures. And one Wasserstein distance computation costs about n cubed operations if n is the number of like Dirac's in my probability measure. Okay, so computing, in some instances, computing a single distance can be expensive, and so you can use these techniques to drastically reduce the number of computations you have to do. Now the principle, I explicitly said I'm not going to worry about how I choose these columns and rows for the previous slide, but you can see it very much matters how I choose the columns and rows, and the overall goal is that I want to choose good columns and rows that represent my matrix well. Really, from a linear algebra standpoint, I want to choose columns that give me the column space and rows that give me the row space of the matrix. So why are we interested in these things, or why is the community in general has used these things in various guises? One is for interpretable representations. If I do a PCA embedding or use the SVD to factorize a matrix, then I'm representing my data in this sort of abstract orthogonal basis, which can be nice. However, it obscures my original features. So my new representation is a linear combination of the features that I have in my data. And so if you're doing something like medical data or something like this, it's hard sometimes to map back to what are the actual features that are most meaningful in your data. And that's what CUR is designed to do. I mentioned kernel matrix approximation. You can use it as a fast approximation to the SVD, and some of the original work from the early 2000s in the computer science community was geared around this idea. And there are a lot of quantitative estimates on how well you approximate the truncated SVD by CUR. I'll talk today about robust low-rank matrix approximation methods. And in a way, if you're a dictionary learning kind of person, you can think of this as finding sort of the best dictionary, but restricting yourself to living within the data set itself. Okay. Some applications, and I'll only talk about maybe a few of these. So subspace clustering, which I've done some work on, which has some other computer vision applications like motion segmentation or facial recognition. Sketching of massive data, I think that's fairly clear from the setup. Image processing, and then NLP. I haven't personally worked in that, but I know some people who have. So here are the themes to keep in mind. Again, this is just a soft introduction to this area. Usually, one way to measure success of a CUR decomposition is to look at the error and compare it to the best low-rank approximation error coming from the truncated singular value decomposition. And so the general principle is that if I want to approximate the truncated SVD of order k, where I keep only the first k singular values, then I need to mildly oversample the columns. So I need to choose some factor p times k columns, and in order to approximate the SVD. Okay? And again, there are quantitative estimates for that. This is a good technique for low-rank matrices or tensors, or ones that are approximately low-rank. If you have a truly full-rank matrix, then most likely these techniques are not going to apply. And then often you'll find randomized sampling algorithms for how to choose the columns, and I'll mention those. We also have some sort of hybrid random plus deterministic sampling methods, and again, as I said, interpretability is a key theme here. So just to give you a little bit of background, if you go search the literature for these decompositions, you will find a wide variety of names that mean the same thing or essentially the same thing. So interpolative decompositions are a slightly more general case where you only choose columns and then you allow the second matrix to be something else. Things of this form where you take column and row submatrices, and then there's a bit of a question what the middle matrix U is. These are called CUR decompositions, going back to the work of these authors and some follow-up works later. You'll see it called cross-approximation, skeleton decomposition, or pseudo-skeleton decomposition. In the case where you have a symmetric positive definite matrix, like a kernel matrix, it's going to be called the Nystrom method, and this has been popular in machine learning since 2000. And then recently there have been some other generalizations. So there's a paper on generalized CURD compositions that I mentioned here. And then, so Michał, of course, has written some nice generalizations of this about metafactorization, sort of giving an overall framework where CUR is a special case, and so are a lot of other standard matrix decompositions. So this middle matrix U, just to give you an idea, so one natural choice for it is the one I mentioned before. It's the pseudo-inverse of that small submatrix. And I say natural choice because the theorem I stated before, it gives you a decomposition in the low rank case. The other natural choice is this kind of strange one here, but if you look at it over here, the reason this makes a lot of sense is these products C times its pseudo-inverse and pseudo-inverse of R times R are orthogonal projections onto the span of these columns and the span of these rows. So I'm taking my data matrix, I'm projecting it onto the columns that I chose over here, I'm projecting the rows onto the rows I chose over here. So you can see fairly immediately that if I chose columns and rows so that I captured all of the column and row space, then I have equality here very easily. Okay. Now this one is easy to compute because this is a small matrix. Pseudo-inverse of a small matrix is cheap. This one is more costly to compute, and moreover, I have to have access to the full data. Okay. For maybe the more mathematically minded in the audience, I figured I would at least state this. So there is a characterization of this decomposition, and this was joint work with Longshu Huang. So take the setup I had before. I have columns, rows, this mixing matrix U, and the following are equivalent. So 1 being equivalent to 2, I showed in the theorem before. And it turns out, so this equality is an equivalence here. The fourth one is an interesting one. We're used to matrices. If I take the inverse of a product of matrices, it's the product of the inverses. That is definitely not true for pseudo-inverses in general. But it turns out that in this case, a pseudo-inverse can be written in a way that I would have been able to do with inverses. Okay. And then the other thing that allows some of our algorithms to work are that it is actually equivalent to just looking at the ranks of the C and R submatrices and those being equal to the rank of A. Okay, so this is so this one drives a little bit of the algorithmic perspective, and then the rest tells you in the exact case where you recover the full matrix, all these factorization methods are the same. But in practice, we sort of default to number 2 here. So how do we choose columns and rows? Well, there are many different ways. Some of the most notable ways are random sampling methods. So the way I'll present random sampling methods here is I make a probability distribution over my column indices, let's say, and I sample maybe with replacement, without replacement, typically without replacement, from that distribution. The easiest case, of course, is uniform distribution on the columns. This takes into account no information about my matrix whatsoever, but is very easy to do. Another one is column length, which is, so I take the Euclidean norm squared of the column and divided by the Frobenius norm squared of the matrix. So I'm prioritizing large columns here compared to small columns. Now, for each of these probability distributions, you can imagine a matrix where it will not be able to capture everything. So maybe I have a lot of small but necessary columns and one large column, so this would be a bad case for that. But nonetheless, overall, you can typically use these things. Leverage scores are based on the SVD. These are sort of the most powerful in theory, but also the hardest to compute because it requires that you compute the full SVD of or the truncated SVD of the matrix. So I have leverage scores of order k. This v sub k are the right singular vectors coming from the SVD, and I look at the row norms of those so that it's v is tall and thin, and I look at row norms and then divided by k. So this is using sort of the most linear algebraic information about my matrix. And another way that you could do it, and this goes back to the work of Drinius, Cannon, and Mahoney, is to use Bernoulli trials on each column. There, often you use column length. It's a little more natural than leverage scores. But there is one caveat. It does require that you rescale the columns in the reconstruction phase, which can be a little bit unnatural in practice. And then some deterministic methods, DEIM, and then there's a greedy selection algorithm from Avern and Boutsidis as well. So some comments on these. So computational complexity, leverage scores is by far the most because it requires computing the SVD. Column length is relatively easy, and then uniform is for free. When you look at theoretical guarantees, how well do these approaches work to approximate the SVD in practice? Leverage scores give you the best error guarantees by far, followed by the others. To get good guarantees for uniform sampling, you essentially need something called incoherence in your matrix, which I may talk about later. And then you have to oversample less for leverage scores than with the other two. And again, it's because you're using the most information available to you. So actually, how much time do I have total?
Yeah, go on.
Like, okay. Do I have the talk should be 40 minutes-ish?
Yeah, approximately.
Okay. All right. So one application that we've used this for is the subspace clustering problem. So this is sort of an idealized cartoon of what this looks like. But the subspace clustering problem in general is I have data lying on a union of subspaces or hyperplanes in high dimensional space, but it's really this union of low dimensional structures, or approximately this. So you can think of a noisy version of this. And really what I want to do is I want to cluster the data. So I want to, with that, I'll assume I know the number of clusters, but if I know I want 3 clusters from this data, I want to take this line as one, this line as the other, and then the plane as the third cluster. Some applications where this occurs, one is in motion segmentation. So if I have a still, or if I have a video, and let's assume the video is not moving, and I have different objects like this plane and Corvette moving around the video, I can extract feature points from these objects and then track where those feature points have been across all the frames. And these can give me something like a trajectory vector for each feature point. And if I put this in, so it turns out that each object will approximately lie on a 4-dimensional subspace of the ambient space, where the ambient space has to do with the number of frames that you have in your video. Okay, so this is called motion segmentation, and one way that this comes up. Some other applications that satisfy in a different way the subspace clustering assumption. If I have faces under differing illumination patterns, each person's face, there's a paper by Basri and Jacobs. They show essentially that if you look at you model the light and use sort of a spherical harmonic expansion, and the first 9 or 10 dimensions will capture almost all the information of a single person's face. So if you have multiple faces, then you have a union of 9-dimensional subspaces where each one is a person's face. So you could use, subspace clustering in this case is facial recognition. And then it's useful in cryo-electron microscopy, where you're trying to, from a lot of noisy measurements, you're trying to reconstruct a protein folding structure. Okay. So here's a combination of theorems from all of these papers. Suppose I have a matrix whose columns are drawn from a union of subspaces. And for the theory side, if I need to assume a few idealized things about my subspaces, I won't go into the technicalities there. One of the conditions is very mild. The other one is a little bit more strict, but there are algorithms that can get around those. Then I can, if I factorize my matrix using CUR or really anything of this form, then I can find an exact clustering of the data. So that's where those idealized assumptions come from. Basically, this matrix X, which are the representation of A in terms of the columns that I chose, that will somehow exactly allow me to figure out what the clusters are. Okay? And there are a variety of works on this, some from an optimization approach, ours from a factorization approach. They all work very well. And the sort of main thing about a lot of these algorithms is that they're fast and robust to noise. Okay. Now, I wanted to talk about more recent work a little bit more from the algorithmic perspective. So I'm going to talk about a specific problem called robust PCA. Now, I will just mention that this is applicable to more things. So you can do these sorts of things for like matrix completion or various other things. But I just wanted to give you a flavor of another practical task that we can apply this idea to. So here in robust PCA, I'm going to assume I have a low rank matrix plus a sparse matrix. So these are outliers or something like this. Just so you have in mind one example of how this could look. Say I have a lot of images of myself. My phone has a bunch if I allow it to unlock by showing it my face. And then I have a couple of photos with me with a mask on from COVID. Well, that mask is a sparse outlier signal on my face, right? It's a small portion of the space, the full space of the image. And if I have a bunch of images without the mask on, then that's just one sparse piece of noise, okay? So the robust PCA problem is to, given a data matrix that's low rank plus sparse, I want to recover just the low rank piece, okay? So the natural sort of non-convex formulation of this is I want to minimize just this difference in the Frobenius norm subject to the rank of L being at most R, which is a parameter that I have to guess. I guess this should be R, I apologize. And then the number of non-zero entries of S needs to be small enough. So here what we're saying is I have n squared entries in my data matrix D, and I'm asking for no more than some proportion alpha of my total entries to be non-zero. So the zero norm is the number of non-zero entries of S. The problem with this formulation, of course, is that it's hard to solve, and it's non-convex. So the original approach by Candes and others was to do a convex relaxation of this, where they replace the rank constraint with a constraint on the nuclear norm of L. So this is the L1 norm of its singular values. So that L1 minimization promotes sparsity, and sparsity of the singular value matrix means low rank. Plus this sort of penalty term, and again, they're using L1 minimization as a proxy for L0 minimization, okay? And then subject to this constraint that L plus S has to be D, okay? This method is easy to solve. It's implemented in all of your favorite programming languages at this point. Although it is somewhat slow for large matrices because it involves solving a semi-definite program. So what we've sort of looked at is how do we take this non-convex formulation, use our ideas of CUR decomposition to attack this directly by making iterative algorithms. Before I go into the actual algorithms, I'll briefly mention these require a couple of assumptions to write down a theorem that says how well the algorithm will perform. You more or less need these in practice. One is that my matrix L is what's called incoherent. So these formulas are in terms of left singular vectors, right singular vectors. You want this quantity mu1 and mu2 to be as close to 1 as possible. Essentially, this means that the singular vectors you want to be non-sparse. So the two extremes for the singular vectors would be the identity matrix, which is very sparse, or a discrete Fourier transform matrix, which is very full. You want your spectrum to look more like the DFT matrix than the identity. That's essentially what incoherence is. And then sparsity is I can't have too many non-zero entries concentrated on a row or a column. So this is a little bit more strict than the one I stated before, because I'm not allowed to have more than alpha on any row or column of my sparse matrix S. So here's one algorithm that we developed to do this task. So basically what this algorithm does, it's an iterative algorithm, and really all it does is it guesses the low rank part by a CUR decomposition. We subtract that off from the original data matrix, and we threshold it to get our new estimated sparse matrix S. Then we subtract that S from the data matrix, compute a CUR decomposition of that, and then repeat. Right? So again, like suppose we can initialize the sparse submatrix to be 0. So the first step is I just do a CUR decomposition of D itself, the data matrix. I subtract that off, threshold, subtract that off, do a CUR decomposition again. So that's the algorithm. There are a couple of parameters. So the first is how many columns do I sample? And do I keep the same columns and rows through the iterative process, or do I resample them? As far as how many columns and rows to sample, I sample on the order of the incoherence times the rank times log n, where n is the size of my matrix. So this does require I have some estimate of the incoherence, which there are some applications in which you can do this. If not, choose as much of a proportion of the columns as you can compute and go that way. And then we sample it uniformly at random, so uniform distribution. And that is because there are some theoretical results that say for incoherent matrices, if I uniformly randomly sample columns, I'm going to, with high probability, capture all of the information of the column space. Okay. And then the other thing is there's an optional step in here. So I can do this algorithm with resampling columns or without resampling columns. So without is the simplest. I just choose my columns at first and choose my rows at first, and then I only ever view those columns and rows. So I only work with this set of columns the entire iterative algorithm, and then at the end, I just do a final CUR decomposition to return the actual result. The complexity of this algorithm, and I'll show some comparisons in a moment. So it's the square of the rank parameter times n log squared n. Most of the other ones, currently this is the fastest complexity that I know of for the non-convex solver by a factor of n up to the log factors. So again, the whole driving force of this algorithm is that we only ever view a few columns of the matrix. That's all we're required to do. So my original matrix could be huge, but I only have to look at log n columns. Okay, so that's really the thing that makes this successful. One other mention, as far from the algorithmic perspective, I never actually do the product of the CUR decompositions. I just work on the columns and rows separately because I never really need them. I can get away with only computing submatrices of them in the algorithm. So again, there are a lot of tricks that you can play where you don't have to actually do all these matrix products. That slows down the algorithm. Okay. Now here's another one that is a little more of a wrapper, but it's fairly easy to understand, and it's the thing that I can prove more about. So I'm a mathematician. I like to prove convergence of these algorithms and things like this. So I thought I would mention this briefly. This is something that uses robust, some other robust PCA algorithm that you like, such as the convex solver, and just applies it directly to a column submatrix and a row submatrix. So before we were iterating over these submatrices, here what we're doing is we just sample some columns, and we'll call this C tilde. So these are columns of our original data matrix with the outliers. Then we sample some rows, And then this thing I call RPCA is your favorite robust PCA algorithm. So if you want to use the Candes convex relaxation, that's fine. If you want to use a different one, that's also fine. So all I do is I return the output of the robust PCA algorithm on my column submatrix. I return the output of the robust PCA algorithm on my row submatrix. So basically, I've cleaned only the columns and rows, and then I just do a CUR decomposition to find the rest. Okay? So that's why I say it's a wrapper. You can use any other algorithm you want in there, and we have some theory that says in certain cases, here's the kind of recovery you get. Okay? Now this one's a slightly more complexity, only really in the R term, the rest are the same. And this is if using a couple of the standard state-of-the-art algorithms called alternating projections or accelerated alternating projections. So I'd like to at least mention what was required for us to understand how this algorithm performs in practice. One is I need to know how the properties of sparsity and incoherence translate to a submatrix. It turns out this isn't so hard, but we have some quantitative estimates. What it does depend on is this quantity, which may seem kind of out of nowhere, but it turns out that essentially a lot of this area requires you to understand what pseudo-inverses of row submatrices of singular vector matrices are. And these can actually be fairly complicated. So this is the truncated SVD pseudo-inverse, some row submatrix of this. And we're able to use some nice estimates from Joel Tropp's work on norms of these pseudo-inverses. Okay. Now I will say his estimates are typically done in the uniform sampling case. Even for other distributions, I don't think it's known how these things behave. I will only focus on this result here. So essentially what we're able to prove with this algorithm is if I sample enough columns, which is again incoherence R log n, and I use an algorithm called alternating projections, which is what inspired the first algorithm I presented, then in this robust CUR framework, then I get relative error bounded by epsilon divided by the condition number of the low rank part of my matrix, where epsilon, where epsilon appears in this algorithm is the number of iterations I need to do in alternating projections is something divided by epsilon. Okay, so if I want epsilon accuracy, I do 1 over epsilon iterations. And this is a with high probability guarantee. So probability under the random sampling process on the columns. So just briefly, so these are again 2 of the kind of state-of-the-art methods. This is the one I just mentioned, and the first one I mentioned called iterated robust CUR. This is a newer one with my grad student I didn't talk about. The upshot is these 2 have the best complexity. I think as of today, nobody's beaten these, but I'm sure somebody will. This one has slightly worse, and then these are n squared so n squared. So speed is kind of more or less this way. Robustness to outliers, that is the drawback of these methods. They're really fast, but they cannot handle as much outliers. So this is that parameter alpha that governs the proportion of my matrix that's contaminated with outliers. If you have more outliers, then you would need to run one of these slower methods. So that is often a drawback of the CUR techniques. If there's too much noise, it gets sort of overwhelmed. Okay. Just to show you some basic experiments, we just ran, this is time versus dimension, which is the size of the matrix. And we go up to 10,000, I think, or almost 20,000. So there's a gradient descent approach, which we're all familiar with doing machine learning. So it works fairly well, but it's quite slow. This was, at the time, the fastest one due to my colleague Hanjun Tsai, called accelerated alternating projections, and then here are ours. And then this is just showing you sampling with replacement, or resampling columns is slightly worse than not resampling columns in the algorithm, but it's not too much worse. And then this last one that we developed that we call Riemannian CUR, it's really something in between. So here we have the accelerated alternating projections in green, and this is time versus the problem dimension. The orange is the iterated robust CUR, the first one I mentioned, and then the Riemannian CUR that's somewhere in between them is same computational complexity in terms of big O as IRCUR, but it's in practice it's slightly slower. And then here you see the drawback of our algorithm. This is the iterated CUR algorithm compared to the others, and this is my x-axis got cut off. This is final relative error after a fixed number of iterations versus the problem size. Or no, sorry, versus the sparsity. So sparsity should go from about 0.1 to 0.9. So you're able to still get reasonable error in the 90% outlier case for some of these other algorithms, including the one that we just proposed. But with just the IRCUR, you can't quite get that nice. And I think this is my last experiment to show you one application of robust PCA is video foreground-background separation. So I have a camera, in this case in a shopping mall, in this case in a restaurant, and it's filming. And at the end of a certain time, I take the video sequence, and what I essentially do is, if my camera is not moving, the background is a rank 1 signal. And the foreground is everybody moving around in the picture, and that's a sparse outlier, unless you're at like a concert or something. Okay? And so when I run robust PCA on this whole video sequence, or video matrix, what I get is the low rank part should be just the background, and then the sparse part should be the outlier on each individual frames. So I wish I had a video of this, but you'll see it in the frames. So here's just the restaurant, here's all the people in this specific frame. And these are from just 2 different runs of our algorithm, I think. And for time comparison, we're sort of orders of magnitude faster than these other things, again, because I only have to look at a few frames and a few pieces of the frames. Okay. So one word on how to translate these to tensors, and I'm almost done. There are 2 natural ways to understand how to use this idea for tensors. Either way requires that I have some sort of core subtensor. Now, I've drawn it with continuous indices here just for you to visualize, but that's not a requirement. But one is I take that little core subtensor, which is this little dashed line, and that's my R here, and then I extend it along every mode. And this works for arbitrary order tensors. It's not just 3 tensors. And then I essentially do a Tucker type decomposition of my tensor, where I have this core tensor here, and then I multiply it along each mode by essentially the product of like a C and R matrix. So this, in the CUR decomposition case, this R corresponds to U, and then these corresponds to the other pieces. You can also do it with fibers instead of these other things, and basically I just I unfold these fibers into a matrix and use that. And then here the blue pieces are going to form the C's, and then the red pieces are going to form the U's, basically. Yeah, this is a typo. That should be U. Okay, so you can do a lot of the same things, and we have some, at least experimental implementation of the robust tensor decomposition, basically. And yeah, so one of our goals is to prove a little bit more about some of these algorithms and extend more to matrix and tensor completion. That's sort of some ongoing work. But there's a lot to do with these techniques and a lot to explore, I think. So hopefully that's been a good introduction to this. So thank you.
Thank you very much. Wonderful talk. I don't know about you, but I'm super excited. I will share my feelings with you. So, allow me. When I heard about these results, I immediately they reminded me about the sensational news that came up when I guess Candace and Donoho were author of when they invented the compressive sensing. The news, the highlights were that you can almost perfectly reconstruct data based on sparse or few samples. And I remember reading that the word miracle appeared in news and in media. And the story behind that was that I guess one of them accidentally, by accident, did not use the Euclidean norm in optimization, but used norm 1 in optimization. They were working with medical pictures, and were trying to reconstruct those images of our brain or something like that. I'm sorry, I can't remember exactly. And it turned out that it works perfectly. Now, what you said now, and congratulations on the complexity of the algorithm, is that you can not only do that, solve the kind of compressive sensing problem related with reconstruction of data, but you can also do that with logarithmic complexity. So congratulations, it's amazing. Now at NASC we are dealing with huge data sets, and one of our core applications is in cybersecurity. And in cybersecurity we very often are sampling network traffic all around the network, and we do that because it's impossible to observe every packet in the network. So quite naturally, we get random sampling, and we're trying to figure out what's going on in the traffic, and possibly find malicious streams of traffic that are dangerous for network resources and so on. So imagine that we can do that, detect malicious streams of packets or dangerous streams of packets, only randomly sampling network all around the cyberspace that we are able to look at, and we can do that with such amazing efficiency. I think that's I'm looking at the team that works on our cybersecurity system, and I think that's the next thing you should do in a few hours is to try to implement those algorithms to try that. So thank you very much for this wonderful presentation, a very inspiring one. Do we have questions? Yeah, Tosia.
Basically, we would just sample. Okay, you heard the beginning of my question. Yeah. Yeah, thank you. So, if we'd like to use it to the matrix completion problem, we would sample columns and rows, then reconstruct them via some matrix completion algorithm, and using your approach, we could reconstruct whole matrix. Yeah.
So that is the idea, and I encourage you to try it. Here's what I'll say. I know that method should work, but I've been working with some graduate students who have been implementing it, and for some reason that I don't fully understand at the moment, it's not quite working how we expected. So there's a possibility that something is wrong in what they were doing, but that was the approach that we tried.
Do you have some feeling, how does it differ from robust PCA?
Well, you can, in some sense, you can cast a matrix completion problem as a robust PCA problem. So that's why I say it should work, right? Because my sparse outliers are just the negative of whatever's in the entries. So yeah, I encourage you to try it. I think again, I don't know exactly why it's not working for us, but I don't think it's because the method doesn't work.
Okay. Maybe it's the implementation.
possible, yeah.
So thank you.
Yeah. So Tosha, when you accomplish these goals, you know where to report the success to these guys. We have a question there.
Yeah. My name is Joanna. Thanks to Carolina, we shake hands, and you know that I work in machine learning. So for me, this sampling and the composition is very similar for the feature extraction, as you also presented in your application examples. So, okay, this is the open problem and very hard problem. How to extracting the feature, minimize the losses of the representation of the whole, things, right? So, first question is, did you estimate any in any your application such losses? So, because this representation is not the full picture of the whole, data set, all the objects. So we make some agreements. We extract the most important features, but the conclusions and the results are then defined for the whole, the full set of data, right? So the first one. And the second question is very connected with the first one because I'm just working with one of my PhD students on some tracking algorithm and tracking problem. So this is one of your application, right? And we have we try to define a good tracking algorithm based on some, analysis of the data, which is multidimensional. So we have exactly the same case, like we have to analyze rows and columns in the matrix, multidimensional matrix. However, we cannot do it independently because we have the realistic data and they are intercorrelation between data. So we cannot ignore it because our results will be not confirmed by the observation at all, and that will be really far away from the practice. So the only probability distribution we could get and try to estimate our models to that is the Gaussian distribution, because we have a strict mathematical model for the convolution of the Gaussian distributions. So my question is, did you consider any other, I would say, methodologies different where such internal convolutions were also considered, or you just assume from the very beginning that you will do everything independently? This is I'm also a mathematician, and I had in the past such a problem, because when we analyzed everything independently, it was good from the mathematical point of view. We got brilliant result. When we tried to validate our model on the real data, it was really a big mess and big losses. Okay, thanks for your presentation, because it was really inspiring also for us.
Yeah, thank you. Okay, I'll try to make sure I answer both parts of your question. So if I understood the first part of the question, you're asking about sort of total error of reconstruction of the original data matrix from these CUR type decompositions. So yes, we've done this experimentally and sort of theoretically. The largest part of the CUR literature has been concerned with that question. The question you have to sort of understand is, how do I measure success and good reconstruction? And it's typically by comparison to the SVD. And that's what I mentioned. So usually you'll get error bounds that say, my matrix L minus CUR and some norm that you like is bounded above by hopefully some small factor times the SVD error. Now the parameters that go into that are, you have to choose more columns to approximate, if I want to approximate the SVD of order 10, I have to choose much more than 10 columns, maybe 20, 30, 100. And then the other thing about those estimates is sometimes they're relative error, although most of the relative error estimates are for leverage score sampling, which may or may not be feasible given how big your data is. If you use column length sampling, then you only get you get an additive error term that's something like epsilon times the full norm of your matrix, which is kind of bad. But that's usually what those methods look like, and they will depend on the sampling scheme as well. For incoherent matrices, there's and uniform sampling, there's a nice paper by Chu and Desmanet in SciMax, I think, that deals with this. For leverage score sampling, it goes back to Drenius and Mahoney and some others. So there's a lot of bounds in there. I think
Embra and Sorensen also give that nice result for DAME sampling in their paper. So
yes, yeah. Sorensen and Ombre have estimates for the deterministic DEIM algorithm. That does still require you compute the first few singular vectors, but it's pretty good. Yeah, so there's a lot there. I was trying to think. I think somewhere I have a table of all these bounds and stuff, but I think it's in an unpublished paper. So I think if you go in my publication site, there's at the bottom, there's something that says this paper was split into like 3 other papers. So somewhere in there, there's a table with all of these, because I did it for myself because I kept getting tired of going back and looking at these papers to sort of see what all the bounds were. So your second question related to what if if I understood you correctly, what if I have correlated measurements in my data and I can't sample independently? We have not done this directly. I don't think I've thought quite about this. A lot of what we try to do is independent because it's easy and fast, and as you say, the mathematics is much easier. I don't know off the top of my head of any works that deal with this, unfortunately. And
yes, that's the main problem.
Yeah.
So make a trade-off. Don't we assume that everything is independent, and in fact, there is not?
Yeah.
So we ignore the intercorrelation.
Yeah.
We assume that they are not important, or we assume that the correlation are important, but we haven't got enough mathematical tools for that, I think. As I said, the only model which is really well prepared and well invented is just the convolution of the Gaussian probability distribution. And of course, you have to estimate everything to be Gaussian. So this is also one of the things. So this is the problem which faces us for many, many years.
Okay. Well, it's a hard problem. Yeah.
Fundamental.
Yeah.
Challenge accepted.
Okay, that's all from my side.
Are there any other questions? Mariusz?
Small one. Yeah. Can we claim the results are really interpretable in case when the columns or rows are chosen and random, in fact?
Well, I think the way I understand these guarantees is the factorization is what allows you to interpret the results, because I'm representing my data in terms of of specific columns within the data. The sampling part of that is I'm essentially saying if I sample enough columns from the right distribution, with high probability, those do give me the right features in the data. So that's how I understand your question. I don't know if that makes sense. Okay.
Thank you.
Thank you.
But I'm not a mathematician, so I'm not even sure it's a valid one. But if it's not, I'm still interested. Why not? You were talking about this column, how to choose the columns, and one of the methods was to prefer the biggest, the longest one, right?
Mm-hmm.
And I was thinking, would it be possible to, or would it make sense at all to make this combined version of the longest and the smallest, the one with this kind of add values or the subgroups. Or I was even thinking about some subclusters and taking the most the biggest or the most representative from them, and then choose them. Does it make sense?
Okay, the second one first. Yes, so in some practical algorithms we have, and we're not the first ones to do this. Many people have done it. We would use k-means or something like that to cluster all the columns initially, and then we choose the cluster center or the nearest column to the cluster center. Okay. So that definitely makes sense, and it works quite well. There's some papers on what's called ensemble Nystrom method. So I do many Nystrom decompositions, and then I average them in a sophisticated way. Well, it's just ridge regression, but I average them, and I get something better. And so they show in that paper basically that if you just do columns, it's not quite as good as if you do k-means and then choose the centers. So that is successful. As far as the question about long and short columns, I mean, really, you can do whatever you want. I just gave you a snapshot of some of the common probability distributions. Okay. I think it can be data dependent. If you know that if you know that large columns are typically going to be the most meaningful, then fine. Just use those. But if you know that you have some small signal that you care about.
It was actually data related, because I had this text representation. I'm working with NLP. I had this text representation where each column was a statistical metric of some linguistic phenomenon, and we used that for classification. So usually it was important how they are distinguished from each other. But actually, I was interested if it would be possible to factorize this matrix to just extract the most important features for this entire for a class of text without comparing it to anything else. Just to see the most important points there in this matrix. And the thing is that some style or text genre or something is characterized by high percentage of some linguistic phenomenon, but lack of this linguistic phenomenon is also a feature.
Okay.
So this is why I was thinking maybe this high, the
yeah, you could probably apply either one of the greedy algorithms or sort of the column sampling from both sides. So you have one distribution where you sample large columns and one where you sample small columns and sort of add them together. I mean, that's one approach. Okay. There is another approach where you can do things iteratively, although this, for small signals that you actually care about, this probably wouldn't solve that exactly, but you can choose a smaller number of columns and then sort of subtract your approximation off and form a residual matrix that's kind of like the error of approximation, and then you can sample for that. So that's another approach that could work.
Okay, I keep you posted. Thank you.
I think we have space for two last questions. Daria?
Hello, my name is Daria. I was introduced, and I have a question about the threshold. In the model that you showed with the iterative, how do you determine the threshold? Is it from the data, or is it from is it the hyperparameter that you put before? So about the more elaborate on the threshold, because
yes,
because I didn't.
Yeah, I was intentionally vague just to make it readable. So in the algorithm where we're doing the hard thresholding, so currently the one I presented today, we don't have a proof that it works for the given threshold, but the algorithm called accelerated alternating projections has a specific thresholding value based on the sort of next singular value of the low rank piece that you're guessing. So it's something that you can calculate without really any extra labor, but it does come from the current guesses. So we can implement that in ours as well. We haven't figured out the right way to change it to make the theory work, but in practice you can do it. I think.
With a little nudge, we can actually try to frame.
Yeah. Yes, but to find the exact threshold, you would have to look at the accelerated alternating projections paper. Yeah.
Okay. Mateusz?
So thank you for your talk. I just want to make sure that I get this right. So if we consider, for instance, multidimensional data, like for instance, I have 4-dimensional data of consecutive measurements of 3D map of the brain, let's say, then can I use this method to extract the meaningful measurements? So to pick the correct measurements and cluster them, for instance, by some descriptive value for each, or I'm just trying to see how can I apply this in my work, because this is.
So let me understand. So you said a 4D tensor,
Yeah.
and each 3D subtensor is volume, like a voxel image.
Yeah.
Okay, and are you wanting to sample like a bunch of those images?
Yeah,
or,
for instance.
The tricky thing about our understanding for tensor data so far is that I have to sample at least full fibers in every direction, and that's so we don't know how to do it just by sampling, a few slices. I don't think. For 3-dimensional tensors, we can sort of do it, but we have to understand the CUR as a T product, which doesn't apply to 4 tensors, I think, as far as, unless I'm mistaken. But so yeah, that's actually something I don't know at the moment how to do, because I really have to have a full fiber. So you'd have to have something over the time, which is, yeah. I mean, you can, if you can subsample along each one, like the image that I showed, but I don't know if that's quite what you're asking.
I will have to think about this more.
Yeah.
Okay. Do you have any questions from Web Network? No. Okay. Yeah. So, what's the weather like in Texas right now?
I think it was, when I left, it was about 80 degrees and sunny. So Celsius, that's probably 32, 30. It's quite warm, yeah. But so I was telling me how in Texas, this time of year, it can oscillate between 30 degrees and 0 degrees in a week. So last week it was almost the same as it is here, and this week it's hot. So eventually it settles in, but.
Yes. So yeah, feels like home then.
Yeah. Yeah.
Okay. And in your work, do you start with application as an inspiration, or is it another way around? So you're in pure maths, and then you see that it can be applied in a given domain.
These days, it's a little bit of both. I don't typically start fully from an application. I consider myself more of a methods person, is how I would describe it. I sort of, I look at the types of tasks that people try to do in various applications, or the things that appear in machine learning journals and conferences, and I try to understand the tasks that they want to perform, and then I essentially go all the way back to the basic principle from mathematics of the problem, and try to work this direction. So I like to start from the core assumptions, the core structure that's there, understand how to solve it under sort of the idealized circumstances, and then understand how to generalize the method to noisy or other cases like that are more applicable.
Have you already tried using for example, ChatGPT to support your research?
No, the only thing I tried with ChatGPT was I asked it to write a 1-paragraph and a 3-paragraph description for a course that I'd already taught. And the alarming thing was that the 3-paragraph description was almost exactly what I had written, which I guess is good for me. Yeah.
I recently played with it, and I asked some exotic question about the relation of projections, and it started answering, and it did that in such a convincing way that really took me like almost half an hour to see what it's missing, and it was really good. Actually, it gave a lot of ideas that should be explored in the process. So, yeah, what are your thoughts on where it is going from the perspective of development of mathematics? How the work of mathematician will look like when there are these wonderful tools such as GPT available?
Well, I think in the broader context of machine learning and AI, you know, a long time ago, I think there was some sort of splitting of math and computer science and things, and now I think they've sort of merged again, and each one influences each other. I would imagine at some point, you know, all of the advances in AI can be brought to bear on mathematical problems, including maybe things that are in pure math that people care about. You know, I don't think we're at a point where you could solve the Riemann hypothesis with a neural network, but you know, I think there's a good interaction there. What I like doing is I like, you know, mathematical intuition and formalism being applied in AI and machine learning, and that's I think it goes the other way around too. So yeah, who knows where? I mean, I hope we don't all write our papers with ChatGPT in the future, but yeah. I guess it's possible.
I think students will.
Well, undoubtedly, yes, yeah. They already are. Yeah.
Do you like teaching?
Yeah, I love teaching. So I've taught a whole variety. You know, in a mathematics department, we always have to teach a lot because, you know, we don't get grant funding for these big physics or chemistry labs, and so I've taught everything from, you know, first semester calculus to I just taught a graduate mathematics of data science course at UTA. I actually taught programming like in Python for the last year and a half. So I love interactions with students, and at UTA we have really good students. We have a new data science program that's a bachelor's degree, and I taught those students for a year and a half in Python, and I was the first course they took, and I didn't run very many of them out of the major, so I count that as a success, and they're doing very well. So yeah. And
in your work, what are the proportion of working with a pencil or pen and working programming, testing?
Yeah, it's probably 50-50. I think you know, sometimes I try to prove things and I get stuck and then I simulate it, or you know, sometimes I have an idea and I simulate it first and then try to see what I can do. You know, my preference is to spend more time pen and paper or whiteboard, because I don't love programming, but these days I have some graduate students who can do the coding for me, which is kind of nice.
Yeah. When you're working on with colleagues and the many authors of a paper, how do you divide work?
Yeah, it depends on the paper. So, a lot of times for me, it's been fairly organic. You know, we talk about the problem and each of us says, well, I think I know how to do this. I think I know how to do this. And we split it up. A recent one, you know, it was pretty clear. I met the guy at a conference that I hosted in Toronto, and I had done this thing on manifold learning in Wasserstein space, and he had done this technique called linearized optimal transport that's like a linearization approach to computing these distances. And then when we said, hey, we should just combine these two, and I said, okay, I'll work on the algorithm part and my part, and his grad student worked on all the stuff they knew about, and we just kind of split it in half, and it came together. So
wonderful. Great. Okay. Thank you very much for visiting us.
Thank you.
I'm sure you'll have a lot of fun in Warsaw. Thank you all for attending. Thank you everyone online. Thank you, Karolina, for organizing and supporting all your team and our other people involved, our technicians. You're wonderful. Thank you. Thank you very much. That's all for today, and see you soon on our next seminar. Thank you.